All right, so today we're going to talk about related rates. Related rates have an application in rectangles, in triangles. You'll see we can use related rates with any formula. All right. We're going to start with the basic ones today, things that you should be able to wrap your brain around. But I will tell you that what will differ in every single problem is the formula that you will use. So you have to read and think about the letters, etc. The other part that's different is that most of the equations we've dealt with only have x and y in them. You're going to see different variables today like p, w, l, etc. And you may see more than two variables within one formula. All right, so let's take a look at number one. Number one, I'm going to try to give you a visual explanation of it. All right, we have a rectangle. It's currently at a length of 8 inches with a width of 9 inches. Okay, so like if I drew a quick sketch, I'm going to do it up here so I don't take a lot of room out of here. Okay, so we can see this as this is going to be 8, this is going to be 9. 8 is L, width is going to be W, but the sides are changing. So that one side could be getting smaller while another is getting bigger, okay, at the same time. The length is decreasing by 3 inches. So what I'm going to do here is I'm going to talk about the length here is 8. It's decreasing I'm going to put a negative there, okay? It's decreasing by 3 inches per second. The width, on the other hand, so here's my information about the width, is shrinking at this rate. Shrinking. 3 inches per second. They want to know what is the rate of change of the perimeter. So I'm using highlighters and trying to connect this because the thing you need to realize is that at any given moment in this rectangle, if L is changing and W is changing, P is also changing. So when it says perimeter, that's going to be my base formula. So I'm going to write that down. So in a rectangle, the perimeter is equal to 2 length plus 2W. If you don't know your geometric formulas, you may need to research those, look them up. I believe the problems that I assigned to you will use the same formulas that we're going to use here, but moving forward, we could talk about different shapes. Okay? Now, when we talk about derivative, when I say derivative, you should think what? Slope, rate of change. Those words are interchangeable. Okay? So if they want to know the rate of change of the perimeter, we are going to take the derivative of this entire equation. So this is the calculus part of it, and then we're going to go back and plug everything else in. So my derivative of P is going to be P prime. My derivative in terms of L is going to be 2. L goes away, so then I'm going to have an L prime. Derivative of 2W is 2, but then I'm going to have a W prime. So now the reason I'm using primes is to simplify my notation. But this is saying this is the change in P, this is the change in L, this is the change in W. So all three of those have a change associated with them. Now I'm going to go back and I'm going to plug my information in to here. What I want to find is the rate of change of P. This is what I'm looking for. This is the same thing as this. Rate of change of P. So I'm going to put in 2 times L prime. So what is the amount that L is changing? What does it say? Length is changing by 3 inches per second. But it's getting smaller. So this is going to be -3. All right, so that comes from the box up here, plus 2, and then my W prime is going to be -6 inches per second. That's all going to equal P prime. From here, we are simply going to simplify the right side. We get -18. But we're talking about the rate of change of the perimeter. Perimeter is a one dimension. Therefore, our units will remain inches per second as the final answer. What we are also seeing in this example is that once we have a base formula, all of the variables have a delta or a change in the variable associated when we take the derivative. Right? So now I'm going to move to the bottom. Let's go down to number 2 all the way down here. I have a rectangle that has a length of 1 and a width of 12. The length is decreasing by 7. The width is growing, so now I have a growing situation here, by 5. But now we want to figure out what is the rate of change of the area. So area of a rectangle is equal to length times width. Here's my little triangle. I can come over here and say that my length is 1. My width is 12. Right. And now we have to be careful because when we go to take our derivative, the derivative of A is A prime. But on the right, this is going to be a product rule. So my product rule says set up, bring down L, the derivative of W is W prime. Bring down W, the derivative of L is L prime. So notice I have 3 rates of change in my derivative, but I still have 2 actual variables that are still there, L and W. They want to know what is the rate of change of the area, so they're looking for this variable here. That's what I'm ultimately solving for. And now I'm going to go ahead and plug everything in. So in this moment, when the story starts about the rectangle, my L is going to be 1. My W prime is positive 5. Width is 12. And my L prime is negative 7. Okay. So I get 5 minus, is that 84? 79 inches squared per second. Any questions on that? Does it make sense? The tricky part is just because we're taking the derivative of L and W doesn't mean it's L prime times W prime. You have to recognize that I'm asking you to do the derivative of L times W, which is the product rule. So you still have all those derivative rules coming into play.